Could this surfer have unlocked the code to the universe?
It's like the hardest problem in the universe to tackle.
Aloha, I'm Lawrence, and this is In the Left Seat. Good morning from the beautiful island of Maui. I'm Lawrence Balter. This is In the Left Seat. We are sitting here at the beautiful Hana Airport on Maui, and I want to introduce our very first guest to this unique aerial podcast experience. If Einstein could surf.
Oh, you had to do that.
And I'd like to introduce Garrett Lisi, PhD theoretical physicist and surfer, windsurfer, paraglider, and today was your very first flying lesson in this beautiful Cirrus.
All right. Garrett, high five, buddy. Nice. That would be my first landing.
It was, not only that, but my first landing ever.
Awesome. Well, you
Yeah.
did great. You're a natural. So I was doing a little bit of reading on some of your background, and it's just so funny that in 1991, you graduated with a degree in physics from UCLA.
Yeah.
I graduated in 1991 with a degree in physics from UCSD.
Ah,
And then you
swapped.
came, and then you came to UCSD, and I came here pretty much.
Nice choice.
What was interesting is how our paths were parallel because you moved here in '99.
Yeah.
And that's when I officially moved to Maui as well in
Nice.
'99. When I was an undergrad, I had a professor who I don't think I could have passed the physics program without Professor Bob Swanson in the physics department. And I remember just before graduation, it was kind of that time where I needed to figure out, do I want to go into physics or do I want to go into aviation or do other things? And I said, what's the hottest thing? Where should a young student ready to, maybe take the next leap go? And he said, try and find the bridge between quantum mechanics and general relativity, and you'll hit a home run.
Someone actually gave you that advice?
Yes.
That's like the hardest problem in the universe to tackle.
Exactly. And so I started hearing about these things in the early days of this string theory stuff.
Right.
And I looked at it and I said, no, sorry, this is not for me.
Yeah.
Tell us your story.
That was a wise choice.
So tell us a little bit about your story, maybe starting from that period, what kind of led you into the graduate program and
Well, I actually started UCLA in '86 or so in aerospace engineering. And because I really love airplanes, and my father was a Navy pilot, and I was really gung-ho to do that and go in and design airplanes. I thought it'd be fantastic. I was about a year into the aerospace engineering program at UCLA, and I was taking all these extra classes, and I was really liking the math classes and the physics classes I was taking. And the engineering classes were great, but they were kind of a grind. And then we had a career day where they took us down, they bussed us down to Teledyne Ryan in San Diego and walked onto the main floor of the engineering unit, and it was just cube farm. Just like hundreds and hundreds of little cubes with overweight engineers sitting at terminals working on designing the electronics for drones, for drone aircraft. It's like, welcome to your career as an aerospace engineer. And I'm like, nope. I think it was the next day I changed my major to physics and math.
wow,
Yeah.
interesting.
So then I got my degree in physics and math. I really loved it because it's like you're trying to get your hands on the source code of the universe. It's like the magical language underlying how everything around us works. It's just that magical language happens to be math.
I'm so glad that you were not in my physics program at UCSD because I saw that you got 4.0 across the board. And you would have changed the curve. I probably wouldn't have passed. so thank you for that.
I really liked college. That's why I was in college for 13 years. I stretched it out as long as I possibly could. So I did 5 years. I took my time, really enjoyed UCLA. Got my degree, and then went to graduate school at UC San Diego. I almost went to Berkeley, but UC San Diego, A, they gave me more money, and B, I got to live right on the beach.
That's why I went there.
It's just like living in La Jolla. Oh, it's just beautiful. I could walk to the surf in the morning, It was just fantastic.
Now, did you interact at all with Sally Ride when she was there?
I didn't. Yeah, no, we didn't cross paths.
I was her first research assistant when she showed up.
Fantastic.
So, yeah,
Yeah.
terrific. So you're in the graduate program, and you are asked, what do you want to focus on, or what kind of led you on your path during the graduate program?
Well, my real love has always been mathematics, and the deepest mathematics possible applied to physics. Because there's really this wonderful interchange in the universe between everything we see and the mathematics that describes it. And mathematicians are always working on mathematics and developing it and understanding it independent of physical reality. But it turns out this whole edifice of mathematics, pieces of it apply to physical reality. We appear to be in a universe that is mathematics come to life. So my real love was in differential geometry, which is a branch of mathematics devoted to high-dimensional surfaces and how they change shape and describing them and their properties in various forms. And that is most applicable to the description of gravity via Einstein's description of space-time as a warping four-dimensional fabric. It's a very natural descriptive toolkit. And then,
which, was difficult actually for Einstein in the beginning. I mean, he had to get
right. Yeah. So, he actually started out not knowing that much about Riemannian geometry. So, as mathematicians that fed him a lot of the knowledge he needed to come up with the theory of general relativity, which is basically an application of pseudo-Riemannian geometry to describe space-time. It's a little different than what the mathematicians were doing, because mathematicians usually work in purely spatial geometries, whereas describe space-time, time is a little different than space. So for time actually has a negative distance associated with it. So for example, a beam of light, when it's traveling from one point to another, it's traveling zero distance because it's going 1 unit of space and minus 1 unit according to the time way it's going, or you can call it an imaginary unit. So anyway, when you square it up to get the total distance, it's zero. So from a light beam's point of view, when it leaves somewhere, it's already gotten where it's going in zero time, as experienced by the light beam. But anyway, so the fabric of space-time actually requires a split signature this way. Mm-hmm. And this led to the theory of special relativity, and then for general relativity, you let this fabric undulate. And it's a wonderful way of describing gravity. It's very natural. And then I really loved that, and then I was learning more and more about particle physics. And elementary particle physics is fantastic stuff. It's really pretty. However, it's not pretty in the same way. It's not geometric the way gravity is. But the universe is just one thing. So it just didn't make sense to me that the description of electrons and quarks and neutrinos would have this more elaborate description that's not geometric. It's in terms of matrices and how things transform under rotations. And space-time has this beautiful description as a four-dimensional fabric. It's like, well, maybe there's some sort of fabric associated with electrons that's consistent with gravity, because the universe has to be one thing, right? It's not just a potpourri, different collection of random stuff. It has to be, one mathematically consistent structure.
So general relativity really has a tough time joining itself with quantum mechanics and quantum...
Yeah, they're incompatible in some fundamental ways.
But you started thinking early on in this path that maybe there's a solution in geometry to bring the two together.
Yeah, that's exactly right.
And so take us through the thought process that now you've kind of solved the problem.
Right.
At what point did you start to see that there's taking the geometry towards the particle world, that this would start to make sense?
I didn't at first. Because, I came at it from the point of view, well, first thing I went to do is like, well, what are the current attacks on the problem? And the current most popular, and even more popular back then, it's been declining in popularity, is the string theory model of how to describe elementary particles in space-time. And to do this, you have basically, theoretically, strands of string that are vibrating in higher dimensional spaces. And you use the vibrations on these strings to describe different particles and their properties. And I looked at this, and a lot of people had a lot of confidence that this is what the universe is. And there are a couple of impressive achievements in string theory, but it seemed like the confidence they had in the theory was way over what the theory could actually do.
Where did it really start to run into problems? Because as you go into higher dimensions, things start falling apart.
So we have the known standard model of elementary particles.
Maybe we should let the audience know we got a lot of pilots in this podcast, so I don't want to lose.
So everything that we see around us, right, is made of electrons orbiting atoms, and the atomic nuclei are made of up and down quarks, which are the fundamental particles in the atomic nuclei. And they're bound together by exchanging photons. But the nucleus itself is bound together by the strong force, right, which binds quarks together. And then every once in a while, if you have a radioactive nucleus, that's often due to the weak force. Okay, so we know about the electromagnetic, the strong, and the weak forces. And we've only found out about those in the 60s up into the 70s, exactly how these things work. And they bind all this matter together, the up and down quarks, electrons, and then there's also neutrinos, which are sort of like electrons, but they don't have electric charge. And they're lighter, a lot lighter.
Now, in the 60s, I believe, correct me if I'm wrong, Higgs was theorizing that there's a Higgs boson or a Higgs field. Maybe, am I correct in that?
Right. So all these particles are described by equations, and in these equations describing these particles, they're all massless. They have zero mass in order to have mathematical consistency. So it turns out Higgs and a bunch of others postulated that there was this background field that all these particles were interacting with in order to become massive. And this turned out to be a remarkably successful theory, but it took them like 50 years before we actually saw the Higgs boson at the LHC, which is a huge achievement.
Okay, so let's slow down a little bit and let's talk about this, because it is a huge achievement, and we should probably introduce the audience as to exactly what this achievement, what it took to get there.
Yeah.
So maybe you can talk a little bit about that.
Well,
I happen to remember about maybe 12, 13 years ago, you did a talk, I think it was here in Maui, and you talked about the Higgs field, and you're saying, we're getting ready to, start proving this stuff.
Right. Well, the idea behind the Higgs is that if the universe is one big consistent geometry, right, and if it starts out in some pretty consistent form, then there has to be some way that it gets an imperfection or something to specify that some direction in this pretty symmetric geometry is special. And then once you have that special direction, everything else can interact with that and become more complex.
And that's broken symmetry?
That's symmetry breaking.
Okay.
Right? So it's like if you balance a pencil on its tip and then let it fall, it starts out totally symmetric. It could fall in any direction, right? But then it'll spontaneously fall in one direction because of however it's set up, or due to just randomness. And once it's unstable, and once it falls, it picks out that direction as steady. And now you can say, okay, if you want to go somewhere, you say, okay, well, let's go that way with respect to the way the Higgs is pointing.
So could one really stretch that out and say that the universe is really a random occurrence because of broken symmetry?
It could be. So there are multiverse theories where people say symmetry could break in a different way. Or you can have different universes with corresponding to different geometry. That could exist. The problem is there's no indication such universes interact with ours. And one of the tenets of science is that anything you propose as a theory has to be in principle testable, or at least give you something useful that you can test.
Okay, so you're taking this, we find the Higgs through an incredible effort at CERN. It costs, what, 10 or $20 billion to get there?
Yeah, it's an enormous collider. It's an amazing undertaking. It's really impressive.
It's the most impressive scientific project we've probably, at least on Earth.
Yeah, it's the largest and most complex machine ever made by humans.
And we have some of the most brilliant minds on the planet working on this.
Yeah,
and
most of them hoping for string theory and supersymmetry. Yeah.
That's what I wanted to get to. So, if you were a consultant to the project, what would you be telling them right now? Because they're revamping to make it a more powerful.
Right.
Yeah.
So there's a proposal to expand the LHC and make a more high energy particle collider in the same tunnel, or to make an even larger collider in the same rough location. And I would suggest that this is a wonderful way to go forward just in terms of pure exploration. It's sort of the brute force way to look down at higher energies, smaller scales, and more massive particles. Because basically these colliders are a big microscope that allow you to look down to smaller distances. And by looking at smaller things, you get to see more fundamental particles and ones with higher mass.
And at these higher energy levels that are required to see this, right?
Yes.
So my question is, how much energy do we need to get to where we start to see general relativity and quantum field theory merge or be able to decode and say, ah, there it is.
Yeah.
I mean, is this where maybe you can take our audience to the journey where you started to work on E8 and explain what that is?
Right. So the thing is theorists have had so much time to work out the description of our universe, and it got harder and harder to look at higher energies with larger colliders. So theorists have gone off and, mostly along the same popular directions, but a few fracturing out. And currently, the standard model of elementary particles, which describes how the electrons and quarks and photons and weak particles and strong particles, as well as the other matter particles that exist as mirror copies of the known electrons and quarks. All of this theoretical structure has been worked out in great detail so that now we can describe things down to incredibly small scale. So anything you might do on an engineering level, we can already describe and know how it works in physics. Okay? It's not going to be probably, for many lifetimes until we energetically have access to anything relating to quantum gravity. Okay?
Which is the holy grail at this point.
Right. So what we have now is a theoretical framework that can describe everything we have experimental access to for the next couple hundred years. But we have an inconsistency in describing gravity using the techniques of quantum field theory. We don't know how to do it. We don't even know if it's the right framework. We just know that gravity is right as far as it goes for describing classical gravity. And we know quantum field theory is right as far as it goes for describing particle physics. And when we try to mix the two, they don't mix well. Because fundamentally, gravity, you're describing the curvature of space-time itself. And for quantum field theory, all we know how to do is describe the interaction of particles in flat space that's not curving. It's just that whenever you do big experiments with particles, you're always in approximately flat space, such that you can't detect the curvature. And whenever you're doing gravity, you're at such enormous scales that quantum mechanics doesn't have any effect, because quantum depends on things being small.
Let's take us back, way back to the Big Bang.
Okay.
And the first, 10 to the minus, 30, 34 seconds, something like that. I mean, is it?
Well, it depends on what you set as your zero time.
Okay.
Theoretically, the universe could have existed eternally before the Big Bang. The Big Bang is just when things were so dense that you couldn't see through it. All the particles were so close they were scattering off each other.
But the point I'm asking is, does the math show where all these fundamental forces, including quantum gravity, are present at that moment, or within the first few hundreds of billionths of a second, or
right?
And then
so
things cool down. What's going on?
That's exactly how it works. So all matter is concentrated to a much higher degree. It's not at a point. It's all spread out. It's just much more concentrated. And at that point, you have very high energies, very high temperatures, with things colliding with one another. And at that early point in the evolution of the universe, at the Big Bang, quantum gravity did have some effects, right? Because you have a lot of matter very close together. Okay, and at that point, it would have been relevant. But yeah, after the first second, after that concentrated state, everything expanded enough and then started clumping and eventually formed into galactic clusters and so forth.
So you decided to tackle a problem that nobody was tackling, called spinors.
Right. So
and maybe let the audience know, what the heck is a spinor?
All right. So if you have normal matter, right? Like you have your phone, right? And you spin it 360 degrees, it returns to its initial state, right? But electrons, it turns out, are not like this. If you want to return an electron to its original state, you have to spin it 720 degrees. Okay?
And that was predicted by the math, or
Yeah,
or
that's what
found in an
it was set up and found first. I don't remember the experiment that first set it up, but it was actually Dirac who successfully proposed a theoretical description of electrons that was highly accurate as spinners. Before Fermi had some ideas with how to transform spinners and describe them this way, but it was really Dirac that laid it out in a relativistic form in Einsteinian flat spacetime.
Okay.
And it's a very, in one sense, it's very pretty, but it's not pretty in the same way general relativity is. It's not pretty in the same way general relativity is geometric, because it's not obviously geometric, because it has to do with these 720-degree rotations that are foreign to the rotations you usually think about for objects, and it's described in this multi-component field that transforms under rotations in this way. It's a mess. So I wanted to know, in graduate school, I encountered these spinners, this description of electrons, which is obviously right. I wanted to know how that links up with general relativity in a consistent way. How can you describe the two consistently? And I went to people in the department with this problem, and nobody was interested in it. Right? It was sort of considered a non-problem. It's like, we have a description of electrons, we have a description of general relativity, that's good enough. I'm like, no, it's not good enough. I want to know, why do they seem not in the same framework? And what is the framework under which they unify? So the first thing I tried, so I got my, so I was in graduate school, I was really interested in figuring out this problem, but no one else was. String theorists, I didn't want to go that way. I thought they were basically in fantasy land. And I didn't think that theories were going to go anywhere. 'Cause the string theory description is they thought they could describe all the standard model particles by tacking on extra dimensions and having the strings vibrate in these higher convoluted directions. And it just seemed like too many pieces kludged on to their structure. And so I didn't like it. But I had invested in Apple stock in the 90s in graduate school, so I had a bit of money saved up. So I'm like, screw it. I'm gonna go to Maui, learn to windsurf, work on physics on my own, see if I can figure this out. So that's what I did, 99. So I came here, found a little shack in the jungle, rented with a friend of mine, and worked on the problem. And the main way I worked on it was a way that it worked in the past, which is to take general relativity, which is a description of four-dimensional space-time, and tack on extra dimensions to it. And using the equations of general relativity with those extra dimensions, describing other force fields. And that worked. I worked on that for like 5 years. The problem was the electrons just couldn't naturally be described that way. But fortunately, after that time, I didn't have any graduate students, and I could look at it the other way. I could just start from scratch and say, all right, well, how do electrons interact with the other forces? Maybe gravity can be included like one of them. So instead of expanding gravity to describe all forces in matter, I started saying, okay, what if I describe all the forces interacting with electrons and then add gravity? And when I looked at that, it looked like a much more consistent structure. So it was around 2004, 2005, I had this enormous algebra worked out where all elementary particles, electrons, up and down quarks, neutrinos, and their second and third generation copies were interacting with the electromagnetic, weak, strong forces and gravity algebraically in one big consistent thing. And this really impressed me. It's like, well, this actually is holding together really well as one object.
Did gravity flow out of this?
No, I had to tack it on.
You had to tack it on. Okay.
It's like, well, how do you, but I was tacking it on within the same framework with the same tools. So it did look like one consistent thing. So gravity.
And this is the higher dimensional geometry that you're.
No, this is a totally different approach.
Okay.
So I put aside the higher dimensional approach, which is called Kaluza-Klein theory. And I tried to then expand the known forces as gauge theories, which describes basically how geometries are twisting over space-time, to also add on the space of rotations of gravity. So once I expanded that set, it looked really interesting just as an algebraic whole. It was all equations at that point.
Was there any aha moment during that time that you thought I might be on the right track?
Not yet. It just looked promising.
Okay.
And at that point, I was teaching here at UH Maui College, and they wanted me to teach full time. At the same time, there's this private foundation started called the Foundational Questions Institute, started by an MIT and Santa Cruz professor. And they started that because they thought that that theoretical physics had gotten too concentrated in a couple of popular areas. So they wanted to sort of branch out and fund unusual research in fundamental physics. And I saw that, so I got my work together, I submitted it as a grant proposal to this new foundation, and I said no to the teaching job. A, because it would have taken all my time, and I wouldn't have been able to work so much on theory, and also it would have cut into my surfing unacceptably.
Absolutely.
So I submitted a proposal, and I got funded for it. So then I had grant funding. I was able to go to a couple conferences and talk about my work. And I was spending time at a friend's house.
Let me pause right there. So you were at these conferences, and what was the reaction?
Usually, when someone walks around and says they're working on a unified theory at a conference, you stand way back. You say, it's like, oh, I gotta go. And that's probably what you should do. It's like if you go to a conference and someone brings up consciousness. It's like, yes, yeah, okay, good luck with that. Yeah. But in this case, I was starting from the known foundational mathematical description of the Standard Model and gravity and just trying to get it all together. I was working from the bottom up. And it wasn't until I was in Tahoe doing some snowboarding, staying at a friend's house, that I saw that this whole mathematical structure that looked like one consistent thing actually fit inside this beautiful mathematical structure called the E8 Lie group.
Now, let's talk a little bit before you dive into the mechanics of that. Tell the audience a little bit about what is the E8 Lie group. It's one of the most beautiful.
Yeah. So this thing is really fantastic. So there's they're basically geometries corresponding to rotations of different high-dimensional spaces. So the simplest one is just a one-dimensional description of rotations in one dimension. The Lie group is called a circle. So a one-dimensional Lie group, circle.
So it's like standing a hula hoop vertically on the street.
Yeah.
Okay, and that's the Lie group.
Well, the Lie group itself is the circle.
Right.
If you have a Lie group that's a circle at every point on a street, right? So you imagine a bunch of hula hoops all over the street. Those hula hoops can be touching at a different angle, and that's called the phase. And how that angle changes over the street, you can describe that with a mathematical function. Okay, we call that a gauge field.
So this is the toolkit.
This is the fundamental toolkit. So, and if you literally use a circle to describe this combined geometry of the street, plus circles attached at every point with phases and waves over the street, this is electromagnetism. So if your street is four-dimensional space-time, how these circles twist in time is called the electric field, and how they twist in space is called the magnetic field. Okay, so it's a twisting of these one-dimensional circles over space-time that gives you a full description of electromagnetism.
Okay.
And photons are quantized ripples of this gauge field.
Which is why they don't have the mass.
Right, they're massless. They don't interact with the Higgs.
So that so far sounds good. So now what happens?
Okay, so we have other higher dimensional Lie groups corresponding to the other forces. So corresponding to the weak force, there's this three-dimensional pretty little Lie group. It looks like a higher dimensional sphere. You attach that to every point in space-time. You describe its three phases of twist, and you get three corresponding elementary particles, which are called the weak force particles. Okay, the weak boson. Then for the strong force, you have an 8-dimensional Lie group called SU3, and that corresponds to the 8 different gluons that bind the quarks together inside nuclei.
At a higher, next dimension up.
Well, it's 8 dimensions up.
Right, okay.
So right now we've got 1 plus 3 plus 8, so we're up to 12 dimensions to describe the forces of the Standard Model. For gravity, you need the 3 rotations in 3 different directions in space, plus 3 different directions you can speed up. Right, and that's so the rotational group of gravity is a 6-dimensional Lie group.
Okay.
All right.
With you so far.
All right. So now we're up to 18.
Okay.
to describe all the forces, including gravity. All right, but now you have to consider that electrons and quarks are also directions if you're just building up this structure this way. And it turns out that this entire framework of of electrons, up and down quarks, electron neutrinos, electromagnetism, weak bosons, strong bosons, the Higgs fields, the gravitational frame, which tells you which direction is time, which is space, and how much. This entire structure, including space-time itself, embeds in the E8 Lie group, which is a uniquely beautiful mathematical object.
This must have sent shockwaves through string theorists, string theory people.
Well, I thought it was absolutely fantastic. I started talking about it at conferences, and then it got...
Did you get any eggs thrown at you? Or?
No, because I was going to quantum gravity conferences.
Friends.
If I went to a string theory conference, it was just a heckle. Yeah. But yeah, the quantum gravity community was very open, and they were doing exactly what the whole high energy theory community should be doing now, which is they were exploring all different avenues, and they were listening to what other people were trying. It's a much more productive search technique than all ganging up in one popular direction and going that way, because you're less like individually you're more likely to be wrong, but collectively one of the searchers is more likely to be right.
In this E8 group, there's some holes in the actual structure itself that predict particles, like the Higgs came out of this E8 group, right?
It's naturally part of it.
Okay.
So you can, like I said, you can embed the whole standard model, gravity, the Higgs, and space-time into the E8 Lie group. There are two things that happen. One is it looked like the second and third generation matter particles. So the electron has a more massive cousin called a muon, and that has a more massive cousin yet called the tau. And these things have the same electric charge as electrons, the same spin, the same rotational processes. Everything's the same except their mass is larger, a lot larger. That's why we don't see them in normal matter, we see them in particle accelerators. But the standard model particles are these three copies of all the fundamental particles. And this is called the three generations of matter. Now I thought E8 has this really pretty symmetry called triality. And when I first saw it, I thought it could be used to describe these three generations. Turns out I couldn't figure out a way to get that to work. I don't think it's possible to work. Now, since then I've been working on higher things that include E8 as a subset, so you can describe the electrons and up and down quarks and electron neutrinos, but I also want to be able to describe the higher generations of particles. And do that, I moved on to larger Lie groups that include E8 as part of them.
So one question that I come up with is, does dark matter and dark energy get involved in the E8 group, or is this something?
It does. Well, dark energy, the most straightforward way...
Let me back up. We're getting way ahead of ourselves.
All right.
We probably lost half the audience now. They've clicked off. Can you talk to us a little bit about dark energy and dark matter, why it's so important, what do we think it is, and where we are with it?
Right. So there are a couple of pretty big mysteries cosmologically with our universe at large scales. So we have this mystery at small scales of how do you have a quantum description of gravity that's consistent. We don't fully know how to do that. There are many different approaches to explore it and figure it out, and there's progress being made in a few of those. But then on larger scales, which is described by gravity, there are also a couple mysteries. One of the mysteries is the universe, from astronomical data, the universe appears to be spatially flat. All right? So if you make a square, a big square in space-time, all those angles are 90 degrees. Whereas if you did that on a sphere, you'd get more.
Okay.
All right. So space itself appears to be flat, but it's also expanding, right? So
that's through observation.
yeah, and that's through observation. We look out there at supernovae that are in far distance, at
Now,
other
this can be a little
galaxies.
confusing to people, and I remember when I first heard of it, it also confused me, because here we are on this sphere that we live on, and we can look at 360 degrees different directions, and so we see things going out like we were told it's like a balloon that's expanding, but you're
Right.
saying now we're seeing that it's a flat universe.
It's a flat expanding balloon.
Flat expanding balloon. Okay. All right.
So you can still think of it as a rubber sheet
Okay.
that's expanding, but it's not curved like a balloon. It's flat, and as far as we can tell, it extends forever.
Okay.
All right. So it's this flat expanse that's expanding, and we know it's expanding because everywhere we look, everything's going away from us, and it's not like we smell bad, right? It's just part of space-time that's expanding, and that not only that, but that expansion is accelerating, and eventually the light from them will be so redshifted that we don't see them. So astronomers a trillion years from now are not really going to know what galaxies are. It's just going to be this one, which is a weird thought.
It's very bizarre.
Born in a different time.
Yeah.
So, but why is the universe accelerating in its expansion? This was a huge shock to see that this was the case. Almost no reasonable physicist thought this would be the case. Everybody thought, oh, maybe it's curled up like a sphere that's very symmetric, or everybody thought, maybe it'll expand for a while and then recontract. But no, it's an accelerating expansion that's going to continue forever. So in order to explain this, you need a fudge factor in the equations to drive this expansion, and that's called dark energy. So you can put it in there as a constant and say, this is, some part of cosmology, the universe is just accelerating its expansion. That's called dark energy. And what it means is that as the universe expands, energy fills in, and this drives the expansion further at an increasing rate. So this is the one place where energy is not conserved in our universe. Everywhere else, energy conservation, you're not going to have a perpetual motion machine. You're not going to get energy out of nothing. You're not going to get a battery that works forever without charging it. There's no way you're getting free energy anywhere except in the expansion of the universe itself. That's the one place it's violated. And it's violated because of this, what's called the cosmological constant.
Which Einstein originally had.
Yeah.
Tell our audience a little bit about that.
So when Einstein formulated general relativity, he had models of what the universe would do under these equations. And it turns out if you get a bunch of matter together, it'll just recollapse on itself. All right, so Einstein actually initially believed in a eternally static universe. So if you twiddle the cosmological constant just right, you can balance this attractive force of the matter against the expanding force of this dark energy and balance them out so everything stays in place. So that's what he originally went with. It's, because the steady state cosmology was a popular idea at the time. And he's like, I'll just go with everybody thinks, and if I put this fudge factor in there, it'll work. Turns out he was right to have this factor in there. He was wrong with what its value was.
That was, he said, was the biggest blunder of his career.
Yeah. And he took it out. So for a long time, the most popular models were without the cosmological constant, without dark energy. So things would just expand from the Big Bang and then recollapse, or they'd expand and run out forever because of the initial expansion was high, but wouldn't accelerate. But with this cosmological constant, it turns out it's positive. It's driving this expansion at an accelerating rate, and pretty much nobody had that bingo table. But that's the universe we're in. So it's awesome that, as much as theorists try these different models, it could be a very unusual model that gets chosen that we're actually in.
Could it be possible that
This is a result of the E8.
Right. So if the stuff I'm working on is right, it means that our universe is a very beautiful, complex, but symmetric mathematical structure that undergoes symmetry breaking and excitation to give us all the matter and complexity and interactions we see around us. It's a really fulfilling picture. I hope it's right.
Okay, so is the theory complete?
Not currently.
Okay. What's missing?
The biggest missing thing is how to describe the second and third generations of matter particles, which I have a better handle on now. And a bigger thing that's missing is how to use geometry to describe quantum mechanics itself. And that's mostly what I'm working on now.
So, is anybody helping you with this, or are you still out
I'm mostly working on my
in the middle of
own.
the Pacific?
I'm mostly working on my own. Especially now we're self-isolating, you know. It's
Yeah.
it's actually, I mean, as an introvert and someone who works on my own, I've been preparing for this pandemic my whole life. I'm good.
You're good.
You can say this is a comfortable distance.
That's
I don't
right.
want to get closer than that.
So, when will you know, or how will we know, or how will science know that this is the correct theory, that this works? What needs to happen?
The most straightforward way is larger, more expensive colliders.
How large do we have, okay. And how large do we have to get to?
It depends on what you want to study. To study more fundamental particles, like if there's forces corresponding to the unification into one structure, whether it be E8 or some other structure that's unifying into, you're going to need probably a factor of 10 in funds and scale, at least to start to look for that.
All right, so Garrett, let's move on to some really cool, fun stuff that you do with your free time.
I'm all about fun stuff.
You created something unique here on Maui, and maybe you can tell the story of what you've done, what you've created.
I think you're talking about the Pacific Science Institute.
Correct.
All right, cool. Basically got this idea from when I was wandering the Earth after I got my PhD. It was really nice to stay in friends' houses without worrying about fixing them or paying for them or doing anything other than enjoying the environment and working on physics. So I really benefited from my friends doing that for me right after I graduated and during my nomadic period.
Those are the friends you're going to share the Nobel Prize with, right?
Of course. So I had this idea that it would be really great if you had a network of places around the globe where scientists could go and work on their research while they, felt supported by a local community and just had, pretty much a nice environment with their needs taken care of. And so I wanted a network of science hostels, because the idea is that science benefits humanity more than any other endeavor, right? It's really through the scientific method and through the work of scientists that we've built up society to such a great technological degree, and largely why life is so good for so many people. And scientists don't get a commensurate amount of support for that in general. Just the way capitalism works, even though they're contributing a lot, it tends not to come back to them because you're very generously giving your contributions away most of the time.
Jonas Salk gave away the polio vaccine. Right?
Yeah. You want to give this away. It's part of the ethos of science. So I think for this reason, scientists need to be better supported. Now, it's nice if that support is directly financial, but it's also support if they have a nice place to come stay in Maui. So I wanted to have a network of such places, but I had a hard time getting my friends to give me use of their houses for other people. So I hadn't got enough resources together to buy a house here in Maui, and have been hosting scientists here ever since for like the past 6 years.
So it's kind of a revolving door of folks coming in for a while.
Yeah, it's really wonderful because I get to be here in Maui, surfing, kite surfing, hydrofoiling, all this fun stuff. And smart people come stay with me, hang out, and enjoy the island. It's wonderful.
Hydrofoiling has a lot of parallels to flying. So
hydrofoiling has been fantastic.
Tell us about hydrofoiling.
Yeah, so it's been one of the most wonderful developments in surfing and kiting in the last decade. Basically, you're in a tiny airplane underwater with a mast coming up out of it, and you're on a board balancing on it. And you basically are flying this little plane, including the roll and pitch and yaw, on a 3 or 4 foot joystick while you're trying to balance it. And if you bring that up too much, you'll breach the surface and then crash. All right? And if you go sideways, you'll flip that thing in the air, and then you have a carbon fiber blade splaying around over your head. It's like being a frog in a blender. You don't want to do that. So the failure mode is just amazing on these things. But they're super smooth. When you get everything tuned in right and trimmed, and you're either surfing along on a wave, or you have got a kite pulling you, or a windsurf sail, or now they have electric ones, right? It's just super smooth because you have this wing cutting through underneath the chop.
You're controlling the angle of attack.
Yeah.
The whole time.
Yeah.
Yeah.
So the whole time, you're tuning everything in to fly along smoothly, and it's just butter smooth and silent because there's none of that, right? It's all just smooth. It's just fantastic.
And you're also getting ready to get your pilot's license.
Yeah, I just started flight training. I've been wanting to do it ever since I was a kid.
Hana Airport, automated weather observation,
So we'll go offshore, and then we'll make a left turn.
4 Zulu.
I wanted to save something really awesome that I could do in middle age when I stopped being able to surf as well.
When you start to grow up a little bit.
No, definitely not growing up. No, Maui is the land of the perpetual man-child. So,
Agreed.
growing up is not on the agenda.
That's great. So we'll leave descriptions below on the Pacific Science Institute, and also some links on some of the work that you've done on E8 and.
Yeah, there's way too much out there about me on the internet. Okay. So and stuff I'm doing.
Well, Garrett, thank you so much for spending time with us today. I'm just such a delight to finally get to know you and now fly with you. And I hope you all enjoyed it as much as I did. And please click the link to subscribe. And we look forward to seeing you on In the Left Seat on our next podcast and YouTube. Aloha.
Thank you, Lawrence. It's been great talking with you and coming out here to Hana Airport with you. Thank you.
Thank you.